Okay, so good afternoon, everyone. I'm Nathaniel, and I'm going to be giving you a bit of introduction to the field of radiomics, what to look out for when you're going to be doing radiomics analysis, and also how to do what we call a feature extraction, which will be shown through a bit of a demo at the end of the slides. So to begin, what is radiomics? Radiomics is the high throughput extraction of quantitative features from medical images, where we can potentially calculate hundreds to thousands of features per image that may characterize disease heterogeneity, and we can feed these into some predictive models. We can take advantage of a lot of different imaging modalities, and then we can also apply these these filters prior to extraction, such as discrete wavelet transform and also the methylation Gaussian filter. We can take all this information and mine it for data, as you can see there. So why has there suddenly been a lot of interest in the field of radiomics in the past decade? If we are able to calculate a value that represents disease heterogeneity, we can better predict diagnosis and prognosis. Radiomics can quantify relationships between neighboring voxels, providing subvisual information to clinicians, which is a really key point. And therefore, we have the potential to represent underlying physiology and build a foundation of causality. And additionally, radiomics can predict alterations within DNA, known as the field of radiogenomics. So there's also that crossover there. And these informative features can be input to machine learning models to predict clinical problems. So here's a typical radiomics workflow here, just a lung CT there. We have our segmented tumor volume here, and we extract these features over here, such as shape features, intensity features, and a bit more importantly, the texture features, which begin to show the relationship between the voxels in there. And we can input these for some predictive modeling, such as here, where it looks like our radiomics features can be used to stratify responders versus non-responders there. Okay, so let's take a little bit of a step back and answer some sort of basic questions. So what is a feature? A feature can be any quantitative value we calculate based on medical image data. The extraction of these features is performing set calculations. So whenever you hear me say feature extraction, it just means we're calculating those features. So some examples that may be familiar to some people, such as a volume or major axis length, pretty common shape features, the rest of set of features, and also mean and maximum, just typical statistical features there. But then they get not so familiar, and we get to our textual features, and they start getting some crazy names like that, such as cluster prominence, difference entropy, and joint entropy. And those are all calculated from what we call the gray level co-occurrence matrix. So textual features attempt to encode spatial information and the values of neighboring pixels or voxels. An example shown here is the gray level co-occurrence matrix. So here we have just our example tumor volume. In a more simpler version, we have a discretized image here, and I'll go over what a discretized image is later on in the presentation. So for the gray level co-occurrence matrix, when we have looking at the first row and first column, we're basically just saying how often is a one next to a one. So not too complicated, and then we go through our image as like this. This is just looking at the immediate neighbors left and right. And so that occurs 4 times, and we just put a 4 there. And we can do the same thing for how often is a 1 next to a 2 or 1 next to a 3, and we populate the matrix as so. And so we calculate those features from that. So now we're going over some factors that affect feature calculation. These include image quality and acquisition parameters, segmentation and to some extent registration, resampling and interpolation method, intensity or gray level discretization, and feature definition. So the battle between in-house software versus open source software. I'll go over those in a bit more detail within this presentation. But above all, just to take home early, report everything and make sure these steps are consistent across your data set. So to begin, image quality and a standardized data set. Those studies may have strict protocols for image acquisition. Mistakes can happen. The technician could just put in the wrong setting, and you get a different reconstruction of using different iterations and subsets. Before any analysis, comb through the metadata of your data set and ensure everything is as it should be. This includes matrix size, voxel size, reconstruction parameters, and so on. Radiomics features are sensitive to changes in these parameters, but depending on which one you look at, it can be a lot or quite a little bit. So we want to ensure that each feature is calculated based on the same image quality between patients, particularly for predictive modeling, because we want all our features to be on the same playing field, so to say. So here's a little bit of example from my master's. We had 24 patients with PET images, and I had a look at what the reconstruction algorithm that was used and also the Gaussian post filter as well. And hopefully it's okay to see there, but those in red are just some of the inconsistencies in the data set we found. The study where the images were taken from weren't really made for radiomics or with radiomics in mind really early on. So that's just something to look out for. Differences in voxel size can be adjusted through resampling, and generally you will be resampling whenever you do this process. And images can be reconstructed if you have access to the raw data, and unfortunately we did not, so we had to exclude some patients. So moving to segmentation, this is generally where we define area or volume of interest on medical images, such as organs at risk or tumor or disease area. Radiomics features are above all sensitive to segmentation, so that's where you get the most variability, and this is what the literature tends to point towards. Feature robustness is often assessed using multiple observers. Large inter-observer and/or inter-observer variability can be used to disqualify features from further analysis as a form of feature selection. And as expected, in terms of feature robustness, it's better to have an automatic and then a semi-automatic and a manual segmentation, but it's not always practical. What is appropriate may change between phenotypes and what has been agreed in the literature. Here's an example of a semi-automatic segmentation process using PET. So here we have this looking crescent-shaped volume of interest, and we place this in the contralateral hemisphere. This encompasses grey and white matter, and we take an average of this volume of interest as our background assessment. Just a process, this is a PET image of the brain, if anyone didn't recognize it. And so we also place a spherical volume of interest centered on our suspected tumor volume. And then we take we apply a 1.6 tumor to background ratio threshold to get this volume over here. So whatever voxels within here, if we divide the value in that voxel by our mean found here, if that's greater than equal to 1.6, that is included over to the right here. And then we had a nuclear medicine physician refer back to the accompanying MRI to remove any obvious non-tumor structures. So resampling image interpolation, resampling may be necessary if there are different voxel sizes across your data set. It is also good practice to resample for isotropic voxel spacing because this gives you rotationally invariant features and increased comparability with other data sets. So there's no clear evidence of using upsampling where we infer artificial data over downsampling or loss of data, but there's a bit of choice in what image interpolation algorithm we use. As an example, we have the trilinear algorithm, the most conservative but can suppress high spatial frequencies. And we have the tricubic convolution or spline, which has high order interpolation, so maybe a little bit more accurate, but you open yourself up to artifacts which can cause out of range intensities. So for binary masks, which is used to specify the area where we want to extract features from our image, nearest neighbor interpolation is best. And so so for anyone who doesn't know what a binary mask is, it's just an image made up of ones and zeros, and that's just showing or encapsulating that tumor area or disease area. Here's an example of some of these algorithms used for, as you said, the downsampling process. That's the trilinear there and the B-spline there. So this might be the hardest spot the difference exercise, but there's a toggle between there, and you look at these high spatial frequencies here, you may see that the B-spline is a little bit sharper, and I've zoomed it in a little bit to see there. And so the trilinear does cause a little bit of smoothing as well. And then this also shows why we don't use the nearest neighbor interpolation for image data, because you get this really bad blocky effect going on in the image. So this is a pretty important step, is the intensity of grade level discretization process. This is required to calculate textural features and establishes relationships between neighboring pixels or voxels. So we have an example of tumor here, and it's all continuous, and we need that to be discrete. So these values are binned to give discretized image over here. So if you have pixels that are close together, like around here, they have been assigned the discretized value of 4. So there are two main methods when doing discretization, although there are some others: a fixed bin number or a fixed bin width. Choice can be modality dependent, it's not always straightforward, and there is no hard evidence for one over the other. But using a fixed bin width has shown better reproducibility in PET, and a fixed bin width ensures that discretized graded values mean the same thing between images with different ranges of values. So which one do I choose? Generally, a fixed bin width is a good choice for both PET with SUV and CT pounds per unit because they're calibrated. You can use a fixed bin width on MRI after intensity normalization, but for images with arbitrary units such as the raw MRI data, a fixed bin count may be more appropriate. Changing the bin number will alter the contrast and image coarseness, and using a fixed bin width will maintain the contrast between images. So what does this look like visually? So image A, we can say is like a high uptake PET lesion, and image B is a low uptake bin lesion. And so the low uptake bin lesion has to populate all the bins you specify no matter what, and you sort of break the relationship with the physiological meaning of the unit you're using, such as the Hounsfield unit or the SUV. But for a fixed bin width, this low uptake lesion will be populating the low end of those bins, and these areas of high uptake will populate the high end of those bins. And so the contrast is maintained, or this is also known as normalizing the intensity resolution across the data set. So if I use a fixed bin width, what do I have to actually look out for then as well? So what should my final bin count be when choosing a fixed bin width? Have a look at the range of values in your data set. There's recommendations that are made to choose a bin width that maintains your final bin number between 8 and 128. Generally, the sweet spot I found to be around about 64. So, for example, if you have a PET image and it goes up to about 10 SUV, if you choose a bin width of 0.15, then that should put you around about 64 bins. But why is there so much fuss? Well, it's because if you have too low of bin number, then your features may be averaged out and lost when you extract them. And too high a bin width, too high a bin number, your features may get too lost in the noise of the image. So software, be aware of the definitions certain Radionics software implements in calculating features. A feature with the same name in two different software may not be calculated the same. So this is an important point when you're making comparisons between studies. Furthermore, some studies may report using in-house software, and unless they provide how they calculate those features in some supplementary material, there may be no way to check it. You can't just dead in the water. So the questions were asked pretty early on, do we need some form of standardization? And what can I do as a researcher to ensure reproducibility with other studies and encourage comparison of results? Along came this fantastic reference manual image biomarker standardization initiative, which includes image preprocessing steps to consider prior to feature extraction. I've gone over this pretty briefly in this talk, but if you really want to get down to the details, I definitely recommend reading it. But most importantly, it standardizes the mathematical definitions of Radionics features. So you can see how, as a researcher, it's really good if I can just say, I'm calculating my features and I'm following the image biomarker standardization initiative. And if another researcher does the same thing, then the comparison is quite easy. And it also has detailed reporting guidelines if you do want to publish a Radionics study. So does software matter? Not everyone wants to create their own software. They usually go hunting on the internet. And so it is extremely useful to have Radionics software that follows the RBSI, making it easier to compare results between studies. Following software conform to these definitions. This figure is taken from a paper detailing from the authors of the RBSI, and they went to all these research teams with their software and gave them reference values for them to see if they could match them and if they deviated. And see, there's a lot of teams here that are conforming to this RBSI. So I'm going to be moving on to how to perform Radiomics extraction. It's going to be a pretty basic tutorial just for those who have absolutely zero knowledge. The example I'll be using is Radionics, which is a free and open source software. And it's a Python package that closely follows the RBSI, and documentation of feature calculation is freely available. So this is really useful as a researcher because I can just say, I'm using Radionics to calculate my features. It follows the RBSI, and the calculations of the features are documented at this link here. And that's all you have to do as a researcher. So if someone else does the exact same thing, then you really don't have to worry about anything else. So alternatively, if you don't want to do any coding yourself, there's the Slicer Radiomics extension that can be found in another build of 3D Slicer, which is an open source imaging software. As you can see, there's a bit of a trend. Everything's free and open source. And this extension uses Radiomics for feature calculation. It is more user-friendly, but less customizable. Hopefully this demo works here. There we go. So this is just using some sample data that Radiomics supplies to the researcher. It's a typical lung CT or lung nodule there. And I'm just sort of showing off there's indeed a tumor volume, and the green area there is the binary mask, as I mentioned, where we're going to extract our features. And so I just quickly go to the module, type in our extension, and I'm already in there, and I load up which image I want and which, or its accompanying mask to do the extraction. And you can see I will toggle what features I want to extract, such as the first order features or features from the grade level co-occurrence matrix, as I mentioned earlier. And we can also resample our images just in this kernel here as well. And we can apply our post filters, Laplacian Gaussian, as I mentioned, and also that discrete wavelet transform, giving us a wide variety of features that we can extract. And then see, I'm also able to adjust that bin width as see as the default in this software. So that's that discretization process, as I mentioned. And we'll just select an output table where our results will be put. And so I've asked the software to do a lot here, so it may take a little while to calculate those features. They should pop up quite soon. There they are. So I'll bring that up for you to see quite easily. It also spits out some diagnostic information, what the version of the software you're using, and what you put into it, like about the image. And so you can see I'm just scrolling through all the features we just extracted pretty painlessly. It's around about 1,100 features all up, and you can chuck those into a predictive model and see how well they predict a patient outcome or some such. So yeah, that's a pretty straightforward process. There's also this here, the parameter file you can put in to have a little bit more customizability, but then you have to have the correct structure and it has to read it correctly, and then you lose that user-friendly part. So finally, how can we measure the quality or strength of a Radionics study? This figure is taken from a paper detailing the Radionics quality score, which is a metric that assesses the reproducibility of a Radionics paper. And so this is what we'll be focusing on here, just up until the extraction process, and we'll extract the images up until here, and then you do some predictive modeling down here, and has a lot of metrics for how you do that. So again, as I mentioned earlier, report imaging acquisition protocols, report everything, and we go on to assessing feature robustness. So multiple segmentations. A phantom study can be used to assess feature robustness of different vendors or scanners, and you look at imaging at multiple time points using a test-retest data set, and that will assess feature robustness to organ motion and physiological change. So you can see how these 3 points are used as basically filters to give you the most robust, reproducible features before you do this predictive modeling step, which I won't go into detail. I think Jake will take on the sort of more predictive machine learning part. So that's where I'll leave you there. So thank you for listening.